Okay, well, I grew up in Ann Arbor, Michigan. I was a faculty brat. My father was on the faculty in the psychology department in Ann Arbor. And I went to public schools, and then for my undergraduate work, I went off to Radcliffe College. And I completed my undergraduate degree there in 3 years, majoring in chemistry and physics, which was a combined major, not a double major. And I wasn't ready to leave undergraduate school yet, so I spent the 4th year there doing a master's degree in physics. And then I went to graduate school at the University of Illinois at Urbana-Champaign and spent 5.5 years there completing my PhD. Then I went to MIT as a postdoc for about 2 years, and then I was given a faculty position here at Chapel Hill, and I've been here ever since 1982. So it's a rather direct path from there to here. I think one of the most important mentors in my career was Professor Millie Dresselhaus, who was my postdoctoral mentor at MIT. And she is one of the grand old ladies of physics. In fact, her 80th birthday is just about this in a few days. And she has been one of the great pioneers, not only in excellence in physics. She basically transformed the science of carbon over her many years, long career, but she's also been a huge leader and advocate for women in science. So not only did she, of course, help me when I was a postdoc by helping me to advance in the quality of the physics that I do and understanding how to be an independent scientist, ever having been a graduate student, but throughout my career she has helped me in a lot of ways. She will often be asked by some national body to recommend people for committees or other kinds of roles within the larger scientific community, and she sort of runs down her mental Rolodex and comes, okay, here's someone for whom this is the right time in their career to take that next step and take on that role. And sometimes that card on the Rolodex has been me. And that's made a huge difference to me in my ability to play a role on the national stage in science. I think the challenges for women are different, and particularly more so in the physical sciences, where women are even more underrepresented than in other scientific and professional fields. I mean, at my level of full professor in a PhD granting institution, only about 6% of the people in those positions in physics departments are women. So the numbers are very small, and the challenge that raises is that people's view of what does a scientist look like, what does a physicist look like, what characteristics, personal characteristics you associate with a successful physicist, those don't match the characteristics that people think of when they think of women, that they're sort of two different sets of characteristics. And they don't think of them as being combined into one person. People will talk about a woman's being a team player, being a hard worker, being dedicated, so all of which are wonderful characteristics, but we associate them more with women than with men. And the male candidates, they'll talk about what a wonderful independent scientist he is, how creative he is, and so forth. Now, the woman may be independent and creative, and the man may be dedicated and hardworking, but the characteristics that will be highlighted in the letters will be different. And so there's just a difference in perception, and as a result, the standard line is you have to be twice as good to be thought to be equal, and I think that's still very much true. The way that people are socialized, it's not because they're venal or wish women ill, but when you think of a scientist, you don't think of somebody who looks like me. When I was department chair, I advanced a project to change the way that we go about teaching our introductory physics classes to have more student engagement, more sort of minds-on, hands-on learning, rather than the traditional lecture. That we didn't change the curriculum associated with the courses, simply how do we deliver that same instruction. And this actually was a project I began before I became department chair, but being department chair was a bully pulpit to move it forward. And we received funding from the National Science Foundation to accomplish this. And what we were doing was, in fact, implementing findings from the physics education research community that have been around for decades. It's a different approach. And one of the reasons why people tend to resist doing this. First of all, of course, it's always a challenge to redo the way you, to transform the way that you do something, including teaching. But also the people who are assigned to teach physics classes are people who have become very successful physicists, have become professors, and the traditional method worked for them. It worked for us. This is how we got where we are, but it doesn't work for most students. The people for whom this is successful is a very small subset, and those are the people who grow up to be physics professors. It's a real small subset of the people that we teach. For, in general, if the students are actually having to think about what they're doing rather than just absorb information as it washes over them, they learn much better. Well, UNC BEST, the BEST standing for Baccalaureate Education in Science and Teaching, is a program whereby students who are majoring in sciences, that be physics, biology, chemistry, geology, and mathematics, can at the same time prepare themselves to be certified high school science teachers rather than having to go on and get additional education. They'll be able to be certified as they leave their undergraduate education. This is tremendously important if we look at who teaches high school science in this country. The problem is particularly acute in high school physics. Less than 1/3 of all the people who are teaching high school physics had, when they were undergraduates, had a major either in physics or physics education, or even a minor in physics or physics education. The vast majority of the people who are teaching high school physics maybe had one course in physics in college, and it probably wasn't taught very well. So they don't have the deep content knowledge that they need in order to be effective teachers of the science. It's tremendously important to get that, to get teachers out there who are really qualified to be effective teachers and also are excited about the subject, and therefore they can get students excited. This class has been more fun to teach than anything I've ever done in my career as a professor. I co-teach this class with Professor Brent Wissick from the music department, and we bring together the physics of how musical instruments work, basically musical acoustics, which is a branch of physics, and how is it that musicians use those sounds in different kinds of musical ideas. So we bring together both the physics of the instruments and how do they work, and also the musician's sense of why would you want this particular kind of sound at this point, and what would you do if you wanted to get this kind of sound, how would you make use of the physics of the instrument in that way. We have a wonderful time. The students engage in hands-on learning. Not only do they do experiments like you might do in a classic introductory physics lab, but they also build their own instruments. They build a stringed instrument and a wind instrument out of whatever they can find lying around their dorm or by dumpster diving or whatever. So these are very unconventional instruments. And then the last day of class we have a concert. Teaching this class has taught me a number of things about the way people learn. And one thing that I've found is that nothing succeeds like failure, which is that there's some ideas that many students don't really internalize and understand, no matter how many times I explain them, no matter how many different ways they read about them, until they have their hands on an instrument, they make an instrument that doesn't incorporate that particular idea, and it doesn't work. That's when the light bulb goes on. So I study specifically the optical properties, but more generally the properties of organic semiconductors. So these are organic molecules which form solids that have the same kind of electrical and optical characteristics that inorganic semiconductors like silicon or germanium or gallium arsenide that we find in all of the electronics that surround us these days, the same kind of characteristics that those materials have, but they are made out of organic molecules rather than inorganic materials. So it's the same kind of physics, but now with organic materials. The advantages to these materials are, first of all, that they can be produced much more cheaply than silicon and germanium gallium arsenide. So you can make them with the same kind of chemical processes that you make nylon and other sort of commodity organic materials. They're very lightweight and they're mechanically flexible. So we can imagine and even move toward making things like solar cells and computer laptop displays on flexible substrates. So you can imagine depositing the material for your laptop display on a piece of flexible plastic foil. So you could roll that display up and put it in your pocket. So you could imagine coating the top of a car with solar cells made out of these materials because it would conform to the shape of the car. So these materials have a lot of promise in that regard of being able to do many of the things that we do now with silicon or gallium arsenide, but do them in ways that are cheaper, are easier to manufacture, and are more mechanically flexible, and so we can put solar cells and displays in places that you couldn't put them if you had something that was rigid and also expensive. Well, the important thing is to persevere, because there's a lot of wonderful things that you can find yourself doing, wonderful ideas to be engaged in. Just it's an intellectually exciting and satisfying field, but along the way you may find some things that discourage you. Simply the fact that you're doing something that not very many people think of as something that women do. That can be discouraging even if nobody comes out and tells you that, which mostly they won't. But I mean, we all get these messages, subliminal or otherwise. So young women should persevere because it's absolutely worth doing, and no matter what anybody may say, young women are as good at this as young men are, and they should recognize that, even if other people are telling them that's not true. It's a wonderful life, and it can be combined with other kinds of things that people might want to do, with family life, with doing good in the world, with making a difference in your community. All of those things are compatible with a science career. And also that doing science is not something that's done by someone all alone in a lab with a clipboard and a lab coat. That science is in fact a very social activity, that you work with people. And so the kind of personal interaction that many people want as part of their professional activity is very much a part of science. And our stereotype of scientists as being loners alone in the lab who emerge every once in a while with a discovery that wins the Nobel Prize, that's not true at all. Science is a very social activity, it's a very playful activity, and it's just a lot of fun.